Good morning. Today we are in the workshop and we are talking about dry cooling. What is a dry cooler? A dry cooler is practically an air and water heat exchanger. It is utilized to cool water, water for procedures, water for industrial applications, or for any kind of cooling utilizing ambient air as the cooling mechanism. It is a fairly economical system, very simple to use, which allows the use of water in a closed circuit and which obviously has limitations because, as you can understand well, using ambient air during the summer period, the type of cooling that we can obtain is a cooling with a water temperature at the outlet of this dry cooler, always higher than the ambient temperature by at least 5 to 10 degrees. Clearly, it has significant advantages because the sole moving electrical component that consumes electrical energy is the fan. Usually the dry cooler is considered a valid alternative to the evaporative tower because it is a much simpler circuit to manage. While in a cooling tower, the circuit is open, and therefore the water we are cooling is directly in contact with the air. In a dry cooler, the water we are cooling is never in contact with the air because this water passes inside pipes. Usually, this type of machines is composed of a finned battery, a finned pack battery that typically has copper tubes and aluminum fins to promote maximum exchange. There are also dry coolers constructed with stainless steel tubes and aluminum fins, or iron tubes and iron fins. Clearly, everything relies on the kind of fluid we need to cool and the kind of treatment we need to carry out, regardless of whether it is a steam condenser or an oil cooler. How do I say? There are so many versions of this air-water heat exchanger. However, it is an extremely simple machine and is used in many cases. Specifically, I wanted to mention self-draining dry coolers. Why are they self-draining? As I was saying, this type of heat exchanger is used to cool water using the temperature of the ambient air. In summer, we don't worry about cooling the water much. The problem is that we can't cool it below 5-10 degrees above room temperature. Basically, if we have an ambient temperature of 35 degrees, our water coming out of the heat exchanger will be at 40-45 degrees. It depends on how we design it and how we have sized it. The problem arises in winter because obviously when we have an ambient temperature below 0 degrees Celsius, if we let simple water pass through the pipes, the problem of freezing arises. In addition, this type of exchangers, designed for maximum efficiency in the summer, can freeze the water during the winter period, even with fans off, due to the chimney effect of the cold air passing inside the finned pack. Water and glycol antifreeze mixtures are used as a result. There are process cases where these mixtures cannot be used on the process itself. I will provide an example of all vacuum pumps. When we cool the water of the liquid ring vacuum pumps, these pumps cannot function with water and glycols, but must be only supplied with water. In these cases, a radiator like this, an exchanger like this, has limitations because in winter it is obviously exposed to freezing temperatures. If we proceed to halt the plant, there is a risk that the water inside the pipes will freeze, causing permanent breakage, potentially damaging the radiator. I assure you that this kind of damage is very heavy and extremely difficult to recover or repair. If only a few tubes break on the outside in the curved area, the repair is easy, but if it breaks inside the fin pack, I would say it is almost impossible to repair. Well, these radiators, these self-draining dry coolers, exist, and now I'll show you some photographs of a couple of these machines. They have the peculiarity that these machines drain automatically, meaning that the water inside the circuit is completely discharged. What will happen? When we go to stop the plant during the winter period for a few days break, for example, for holidays or a production pause of the plants, we will simply open some valves and completely drain the water inside the heat exchanger. In this manner, even in the event of frost, naturally the heat exchanger will not freeze and will not incur damage. As can be observed from the pictures, in order to accomplish this outcome, the exchange package is typically installed at an incline, and there exists a specific circulation that enables draining, that is, fully emptying the water inside the exchanger. In all other instances, a combination of water and antifreeze is utilized to completely prevent freezing. On these machines, fan technology has been greatly developed, both to limit the noise, since they are machines that are typically installed on roofs, in outdoor areas, and therefore with easy noise diffusion, and from an energy point of view, by seeking out highly efficient fans in order to minimize energy consumption as much as possible. The maximum performance is achieved by using fans with electronically controlled motors, the classic EC motors. Why is that? Why do we go to do a speed check based on environmental conditions? As I said before, they are machines designed to have maximum efficiency during the summer period, when the ambient temperature is very high. In winter, this high efficiency enables us to get rid of a significantly larger number of kilowatts than we actually require. Consequently, we are able to adjust the fan's speed and, in turn, conserve electrical energy on the motor, causing them to operate at an extremely low speed and thereby restrict noise while definitely decreasing energy usage. Fascinating subject, don't you think? Regards.